Lab 3, magnetic fields. So in this lab, our goal is to measure the distance dependence of the magnetic field of a bar magnet, and also to compare the accuracy of the measured values in the experiment to those computed by the computational model. Concepts covered in this lab include magnetic fields, so Biot-Savart law, and I put some of the formulas for shown right there, and superposition of fields as well. Data measurements and calculations. So basically what we can discern is that the larger the distance from the bar magnet, the smaller the Bx value, or the magnetic field X component value. So for each one of those intervals, so 20, 70, 120, 170, 220 microteslas, the distance was recorded, as well as the reading from the phone magnetometer of the magnetic field strength in teslas. So from this, the spreadsheet was used to create a graph with a line of best fit equation, which is right here. Y is equal to negative 3.5152x minus 15.55. And we can get from this that the distance dependence, n, would be equal to negative 3.5152. And taking the intercept from this, negative 15.55, and solving using the formula shown above for log natural of k, gives that the k would be equal to e to the power of negative 15.55. Plugging for all this and solving and using the Biot-Savart law and getting the magnetic dipole moment, mu, gave a value of 0.882 Newton meters per Tesla. So this is the output of my computational model. And in this model, the orange arrows pointing towards the right, in this case, are the magnetic field on axis representations, and the blue arrows are the ones for the perpendicular axes. And there is one more blue arrow behind the middle one, but it's blocked in this view. And in the top right, the small green arrow is the magnetic field vector of the magnetic field at 45 degrees at distance d from the bar magnet. So this is the coding that went into creating the computational model. So in this part, the initial part, this is some of the initial values that I have to input, such as the magnetic moment of the magnitude of my magnetic moment, which is 0.882, and this was the function created for the magnetic field. So as you can see, I plug in the value of mu as well as the value of the distance r, and I calculate a magnetic field strength at distance r. This section right here sets up 6 observation locations, 2 of them being on axis with the magnet, and 4 that are perpendicular to the axis, in order to set up for the next part of the code, which creates the arrows at those sections. So right here on the left, there's 2 arrows that are created that are on axis with the magnetic field, and those are orange, as I showed earlier, and these are the blue arrows that are perpendicular to the axis of the magnetic field. And right here, you get the average of the perpendicular distance from my experiment and plug it in to get a d value here for the 45 degrees from the axis value of d. And I create another arrow to represent the magnetic field, 45 degrees from the axis. Now, so if I hadn't oriented this experiment to compensate for magnetic north, and instead I just laid out my meter stick at some random angle with respect to Earth's magnetic field, my result would have changed because, so in this experiment, when we account for magnetic north, we take this into account by making sure that the measured magnetic field on the X component from the magnetometer chip was equal to 0 teslas. This means that the only magnetic field measurement being recorded wasn't being skewed by the Earth's magnetic field, and instead it was only that of the bar magnet. So if this wasn't done, the measurement would change because there'd be an X component of the magnetic field of Earth affecting the total value, and the results would be skewed because of that. And if we were to stick 2 identical magnets together end to end and run the experiment again, there would be a magnetic field of a stronger magnitude, not necessarily like twice as strong, but it will still be a stronger magnitude, and the values of the field strengths that were measured would be greater.